We're honored to have Katie Driggs-Campbell. Katie's an assistant professor of electrical and computer engineering at the University of Illinois, Urbana-Champaign. She got her PhD from UC Berkeley a couple of years ago, I think 2017, working with Urbana-Champaign, and then worked on a postdoc at Stanford in Michael Kokendorfer's group. She works in the areas of human-centered automation and autonomous systems, and really brings in techniques and tools from control, robotics, machine learning, and human factors. So it's a pleasure to have Katie give this talk today. Thank you, Katie.
Well, thank you for that kind introduction. So again, my name is Katie and I'm an assistant professor here at UIUC. Today, I'll be presenting work by two of my students, Peter Du and Tianchen Ji, as well as some work from collaborators from Stanford in Michael Kokendorfer's lab, as well as here at Illinois, including Girish Chaudhary and a little bit from Cheyenne Mitra as well. So to just give a little bit of context, my group typically looks at how to design safe autonomous systems that have to operate out in the real world with people. So a lot of our work typically looks at how to both model human behaviors and integrate this into the design of our systems. But today we're going to be mixing it up just a little bit. So instead of looking at basically how we can design successful systems, we'll be kind of flipping the problem around and really trying to think about how our systems fail and think about how we can basically use this in our design process. So really thinking about capturing and identifying these failures so we can assess safety, assess performance, and hopefully inspire some new ideas. So I really enjoyed George's talk at the end of the last session. In particular, I really liked his discussion on how typically we look at things that are very structured, but a lot of our systems, we want to operate in very unstructured environments. So I love this point. And one of the things I really like to discuss when I first open up this talk is the importance of context and how structure affects the problem overall. As some examples, some of the projects or applications my groups looks at ranges from manufacturing to transportation and agriculture. And one thing that you'll note in these different applications is you have widely different sort of context cues and very different amounts of structure. So if you'll allow me to make a few sort of sweeping generalizations, we can kind of see this notion of increasing structure as we go through these different applications. So in the manufacturing context, you have a lot of control over your environment. The processes are really well defined. Some people would barely call this, or work in this area, autonomous. It is more of an automation piece. And a lot of the research and sort of open problems in this work is actually sort of trying to decrease the structure in this space. Sort of if you move down this line, if we think about the autonomous driving domain, you have very well-defined rules of the road. You can clearly define the behaviors you want, what a failure is, but there are many situations where you might have some sort of leakages or a breakdown of that structure. So either through interactions with human agents or some assumption violations. And if we go to the very far end, sort of thinking about an agricultural or generally a field robotics type domain, this is an area where the environment itself is constantly changing. One thing I learned since moving here to Illinois is that you can actually hear corn growing. So it grows so fast, you can actually hear it. And when you move to these, very unstructured settings, even very simple assumptions that you might make in typical robotics type environments might not hold. So simple things like GPS might not be available. So when you really think about trying to find failures or characterize the types of uncertainties that you might encounter, it becomes really, really difficult to actually characterize them and then turn it into something that's actionable. So as we look at these different sort of applications and we think about what robustness, what safety, what these things mean, it becomes sort of important to really think about how we can really quantify or think about the structure. So today we're going to be primarily thinking about the failures that we've found, primarily in the transportation domain. And then depending on timing, we might have time to squeeze in some of the ag results. But for now, we'll be focusing on the failures we've encountered, basically how we've designed these robust systems in the transportation domain. And we'll look at some different settings for finding or identifying these failures. So first, we'll look at some real-world experience that we've encountered, real-world failures. We'll look at simulation, and then the case where we have almost no structure, so we look at anomalies. So we'll go ahead and get started with this real-world experiments. So this is primarily building off of the work that I did while I was at Stanford, finishing up my postdoc. And this is where we got to work with a real test vehicle. And our goal was to design an autonomous vehicle that could successfully operate in urban environments. So from when we were working on this project, we were designing the full pipeline, but primarily focusing on the decision-making and control aspects. So again, instead of focusing on sort of the end result, where we could have the system driving in our little test facility, let's look at some of our failure cases. So we're going to first look at a few of our intervention scenarios. So an intervention is basically scenarios where it goes from being in fully autonomous mode, and then there's an unplanned switch to manual mode where the safety driver determines that something is going wrong and intervenes. Okay, and let me get my laser pointer out to make this a little easier. Okay, so in this first case, so here we are practicing some lane changes here. So this is our vehicle here. You can see it's LiDAR view. And this is the front view of our vehicle. So you can see we're about to overtake. And at some point, we'll just sort of start careening back towards this agent. Student nicely taps on the brake and resumes control. Okay, so this was a relatively simple and luckily low consequence failure. And this was primarily due to model mismatch. So this was a scenario where the vehicle itself thought it could basically merge back behind this vehicle. But there was some mismatch between basically what the system thought it was controlling and the real vehicle. So it wasn't actually able to complete the maneuver. So we think that was the primary cause of this failure. But there's also some other sort of interesting things at play here, where there were also some competing objectives. So the vehicle both wanted to maintain some speed, so overtake the car so it could maintain it, but also it had to take a right turn in a short bit. So there's some some not playing very nice between the two objectives here. Okay, and here's another one. So here you can see we're at an intersection, and if you'll see there are some bounding boxes here of detected agents, but you can see it's sort of flickering in and out. And as you can see in this camera view, it's a little bit hard to see what's going on even from human eyes here. So in this case, the perception system was not doing a great job. And at some point we just sort of started sitting here and we decided to take control here. So again, this isn't a necessarily disastrous failure, but this is a case where there was some sort of misunderstanding or some things that weren't perfectly captured in the perception system that led to a failure in the decision-making pipeline. So the cause of this failure was some perception uncertainty. And actually one of the big challenges in this space is really having a good characterization of the types of failures and a good model of the uncertainty for some of these more complex perception systems. And so basically that led to some downstream effects. So these are sort of a few of these, a few example failures that we had. And once we encountered them, we can take them into account and start fixing them. And typically when you have these sorts of problems, so you have something like model mismatch or some uncertainty in your system, you start turning to things like robust decision-making and control to help account for some of these phenomenon. Okay, so this is a very classic problem. So basically, if you want to safely and efficiently control some vehicle, it'll be governed by some dynamical equation. You want to find the input that will help you achieve your goal or stabilize your system. And often what you do is you try to capture all of your uncertainty or your disturbances as some function that's basically added to the right side of the equation. And this is a sort of fundamental and a really sort of key problem from control that has been studied for a long time. And this does a great job of capturing some of the things that we did encounter on our vehicle. So this is great for capturing things like sensor noise or environment and uncertainty, where you basically want to be able to say, given some worst case noise, try to make sure that you can still effectively control your system. This is also really good at capturing some of these unmodeled phenomena. So again, getting back to that model mismatch, this can say maybe capture some nonlinearities in your system that you maybe aren't capturing in your nominal dynamics model, or account for just some other mismatch. So again, this is something that has been studied for a long time from the control perspective, and is becoming more important as we start using more learning-based systems, where perhaps we are training in simulation and then trying to transfer to a real vehicle, or if you have some training data set and it might not exactly match your test scenario or your data at runtime. So using this sort of formulation to try and capture these sorts of uncertainties or mismatch is a great way to kind of try to avoid or mitigate some of the concerns. And as an example failure in this model mismatch case, so if you were like us and immediately tried to look at try some learning-based controls. Let me see if I can click this correctly. Let's pause really quick. So here's an example where we tried to do end-to-end learning on the vehicle. So we're doing a weaving maneuver. So our car will be the one that we're following here. You'll be able to see the LiDAR and sensor view of the agent here, and the front view as always. And we're trying to learn some weaving maneuvers. So we're going to basically try and weave through these static obstacles. We're spoofing the sensors, so there are vehicles in front of it. You'll be able to see some cones, and you'll see why we don't have real vehicles in a moment. And again, so we were trying to test out some learning-based control. And again, this sort of captures some of the phenomenon that you observe when you have some of this model mismatch in learning cases. So you'll see we start sort of having this compounding error, some unstable scenarios, where we slowly start sort of edging or oscillating more and more and getting into these collisions. So this is a fairly common phenomenon. So people who played with learning control will know that some of this mismatch is a problem. But if you start capturing some of these uncertainties and looking at the robust learning techniques, you can start really thinking about how you can push down these failure rates and really start sort of capturing good performance, perhaps sacrificing a little of sort of peak performance, but ultimately trying to combat some of these issues. So again, based on our experience and sort of just doing this sort of iterative, see where things fail, fix the system, you can you can produce a system that is able to effectively drive. We won't look through all the videos because it's actually kind of boring. So I think, finding people that are driving safe is not the most exciting thing to watch. But this sort of robust formulation is really important when you're thinking about how to design these sorts of systems. But so far, the failures that we've been talking about thus far are mostly capturing these sorts of uncertainties or mismatches, but they didn't really capture a lot of these sort of high risk issues or scenarios that we think about when we think about failures in autonomous driving. Often these failures that we think of are sort of the more high risk issues really come from things that arise from interactions. They really are more on this sort of collision side of things. But these sorts of issues are often actually very hard to find once you've accounted for all of these sorts of issues that you might have. So once you have a fairly robust system, it becomes a lot trickier to find these sorts of failures in the real world. So that brings us to our next topic, where we now trying to look at these more interesting failures. And we're going to turn to simulation to sort of help us find these sorts of scenarios. Okay, so just as a little bit of motivation or more motivation for why we might want to look at simulation, a lot of safety critical systems, and in particular autonomous driving, suffer from this issue where a lot of the high risk events or the collision situations or these sort of these key failures that we want to find are also very low probability. So if we look at human driving rates, so if we focus on the bottom two pieces here, this is the collision rate and the fatality rate for human drivers. And I think everyone's sort of seen some statistic like this at some point by now. But we can see that this rate is actually pretty good. So human drivers rarely get into collisions and rarely, even more rarely, actually cause fatalities. So when we start thinking about trying to find failures in a system that should work, or if we want to try and show that our system is as good as human drivers, to be able to actually get a substantial estimate or really think about if we are better than human driving, we're going to have to drive orders of magnitude more kilometers than this to make sure we have a statistically significant sample. If we were to actually think about doing this on real systems, it just sort of becomes infeasible very quickly. So one thing we'll find is not all miles driven are equal, and it becomes very sort of difficult to do this in real systems. It's both inefficient and not very economical. So to help this, some people, or we often turn to simulation to basically help fill this out. There's one common saying though, and it's that everything in simulation is doomed to fail, or doomed to succeed. Oh, I'm sorry. Everything in simulation is doomed to succeed. So now we really have to start thinking about how we can push our simulation to help us find failures. So let's really quickly think a little bit about how we might start thinking about how to design simulations that can help us find these failure modes and help us understand our system a little bit more. So if we were to look at a relatively simple situation, so let's say we have an autonomous vehicle that we are interested in testing or finding failures for, and we're going to test its interaction with a pedestrian. So if you were to do traditional simulation-based testing, many simulations involve constraining some trajectory and doing something like gridding a velocity to find results. So you basically discretize this motion and project it forward and start capturing more some behaviors that the pedestrian might exhibit. You can start having more expressive models. So maybe you can start sampling more behaviors. But at the end of the day, typically these simulations will ignore some possible, although maybe unlikely, trajectories that could lead to a failure, something like this. And normally the way we design simulations, it's hard to know if this sort of behavior, it might seem a little wonky or uncertain, but it's hard to know if this is something that is useful or not. Additionally, as we start thinking about more complex situations and start adding more agents to the simulation, it becomes, you get this sort of combinatorial explosion very quickly. So it becomes very difficult to effectively search or sample the space. And really what we want is to be able to probe this system and run these simulations so we can very quickly and efficiently find a failure while we're finding one that is also very likely. Okay, so the way we have started to address this problem is to look at different testing techniques, like adaptive stress testing. And basically what adaptive stress testing is going to do is it basically helps us probe and search our simulation and encouraging it to basically find these high probability but failure scenarios. And the way we do this is we actually cast the validation problem as a reinforcement learning problem, where our learning agent is actually our full simulation. And we're trying to probe and basically cause our system to drive it towards failure here. So here we have this simulation, and depending on basically the level of transparency, you can have very black box or very white box type simulations. As long as you provide some sort of estimate of the likelihood in some event, flatten it out. You can tune your reward function, which we'll talk about in a moment, and use your solver to basically help find these failures. So we design our reward function to basically encourage it to find some failure. So we give a high penalty for not finding a failure, and we penalize it for not searching these high probability actions. So at the end of the day, this is going to return some example failures where we have these high probability examples out. So let's look at a quick example. So let's go back to our pedestrian case. where here we have our simulator that has our system under test. So that's going to be our autonomous vehicle here. And some pedestrian agent that we're trying to basically test and probe and use as our possible cause of failure. So in this case, we are going to be controlling the behaviors of our agent as well as some noise in our sensors. So basically we can try and find these failures that really circle around this pedestrian agent. And as I mentioned before, we're going to basically use reinforcement learning solvers. And there's a bunch of different solvers that you can use to basically act as a efficient search mechanism. We often use Monte Carlo tree search because it gives us some level of interpretability. So it gives you a little bit more insight than you would typically get from some of the deep learning type solvers. And it also has some nice relationships to other testing or verification techniques like statistical model checking. So at different points in your simulation, you can actually start using these other tools and doing things like querying risk along the way. But again, so what this is going to do is this is basically going to allow us to start probing our simulation and finding these example failure cases. So again, if we were to just take a traditional simulation-based approach and run our simulation a bunch of times, we would get this very nominal behavior out, or these expected situations between our vehicle and our pedestrian. So we'd almost always find these sort of nice situations. Now, on the other hand, if we were to just look at worst case or adversarial examples, we might just get something that isn't actually very insightful here. So we'll just sort of get this very reckless pedestrian agent that is sort of just trying to get into a failure. So it might not actually capture the situations that we're actually interested in capturing. So one of the big questions is, how do you actually find relevant failures? So by basically designing this system effectively and iteratively tuning this, you can start finding more useful and relevant failures that can actually help you in the design process. So you can do this partially by tuning your reward function and partially by setting up your simulation correctly. And at some level, that sounds like a relatively simple fix. But one of the things that we found is when we're transferring or working with this tool with our industry partners is having this sort of easy interface through something like a reward makes it very easy for them to understand what's going on, basically how they can use their system. So being able to sort of quickly tune some of these parameters has been very effective, again, when transferring this into practice. So we've been able to search and find a number of failures here. And one of the key insights that we found was that there's one of the major issues is when we have some failure in the pedestrian or predictive modeling pieces here. So after sort of working on this validation piece for a while, one of the things that came out of it was a little bit more effort in thinking about how vehicles and pedestrians can interact. And this has led us to some cool work in collaboration with Shai and Mitra, where we're able to have designed some new pedestrian intent and prediction modules and close the loop on a safe system here. Okay, so that's all I have for the simulation piece. Since I only have a few more minutes left here, I'm going to go fairly quickly through this anomalous case just to sort of show some fun videos. But again, I think one of the key things I'd like to highlight is that while I would like to say that some of these tools and things that we've developed for assessing safety would work in all sorts of scenarios, often they do require some model or some sort of way to represent the environment. And that has been one of our biggest struggles as we've been moving to different sorts of situations like this agricultural case here. So to just sort of highlight some of these sort of stronger issues here, we'll just talk about some of the field robots that we've been working with. So this is a robot that's now a part of EarthSense, which is a startup out of UIUC. And this is a robot that's meant to operate out in the field and monitor some of the crops as they grow. And one thing you'll notice is even though it's sort of moving up and down these rows with apparent ease, currently they all sort of require this babysitter. So you can see, I've paused it here where we have this person that's watching the robots. And to really move it to the next sort of higher levels of autonomy and give it more capabilities, we need to start basically helping it come up with tools or design these tools so it can recover from even simple failures like this. So we don't always require someone to sort of come in and intervene. So to just highlight some of the issues here and sort of talk about why this problem is hard, here's a case of sort of normal behaviors. Looks like this video might not be playing very nicely. But this is sort of normal operation. And as you can see, this is fairly different from a sort of well-controlled or a clean environment. So coming up with new tools to be able to characterize or understand the sort of failure modes or even the sort of nominal driving behavior here is very challenging. And if we look at some common failures, you can kind of see that even just visually, it doesn't actually look that different when you're in these sort of failure conditions and when you're in normal driving. So coming up with ways to represent or characterize failures in these highly unstructured and variable environments is quite challenging. I'll just sort of skip through some of this. We've been working on anomaly detection and new frameworks for doing these detections. So we can still characterize or understand these scenarios. So we can do some online detection and sort of understanding what is going on with the robot precisely. As a quick example here, here's a case where our system is able to detect some anomalies, so something it's never seen before, a wild grad student. So we can see we can use anomaly detection to basically identify these situations. And we can start sort of doing some wrappers around this so we can start incorporating things like recovery maneuvers. So once it encounters some failure, now perform some recovery autonomously. And we can also do some active probing. So once we have a deeper understanding of what sorts of failures and what the situation is, we can basically start trying to make better inferences of what's going on. Okay, and since I'm almost at time, I'll quickly conclude here. So thanks for listening to me talk about the different failures and how we've been sort of actively searching for these failures in a variety of different settings. I'd like to thank all of my collaborators and sponsors for all of their help. And with that, I guess I can take a question if there's time.
Thank you very much, Katie. That was a wonderful talk. And thank you for presenting in these domains that you've been working in, this concept of the importance of failures and then the analysis that you're building around that. I think we have time for 1 or 2 questions. And so as before, please either unmute yourself and ask a question, or you can also ask questions over the chat.
Catherine, I'd like to ask a question. A wonderful talk, first of all. I think you touched on a point that I think we perhaps would be the panel, which is, and I think Hadas brought it up as well, which how do we measure safety and how do we perhaps demonstrate safety to the outside world? So what would be your answer to this based on your wonderful work? And I'm just trying to get a sense that we all prove theorems or have verified constructions or whatever. But at the end of the day, you know, how do we compare to integrated systems? You know, I mean, I think that to me is something that we as a community need to articulate better and demonstrate better going forward. And I would like to get your thoughts on that.
Yeah, that's a great question. Yeah, so I don't think I have a really great answer other than I know that this is really hard, and especially even in relatively well studied areas like autonomous vehicles, you'd thinking about collision rates or something like that would be a good measure of safety. And when we think about human driver safety, this is often what we think about. But I think as you're probably hinting at, this really isn't the best measure, and for a few reasons. One is because not all miles are equal. So 100 miles driven on a highway and getting no collisions is very different from driving 100 miles in a parking lot. So parking lots are actually one of the most dangerous situations for driving in terms of collisions. But yeah, so it's not actually capturing the heart there. I think another sort of point to that is For autonomous driving, back in the sort of early days of the Google car, while they were never at fault, they were getting rear-ended at a really high rate. So even though they weren't causing failures, they were still sort of getting into these situations where they were causing changes. So I guess I don't have a strong answer other than hopefully we'll discuss this in the panel, because I'm really excited to hear what other people have to say.
I mean, it could be that your talk suggests that how easy it is to break them is a measure.
Yeah. So if there's like a good measure of robustness, or even just analyzing the most likely failures, does give you some insights about whether or not it's something that's sort of you're at fault, or if it is something that is deeper.
Thank you.
Thank you. And thank you, George. Any other quick question for Katie while we ask Keenan to get ready to present the final talk of the workshop? Okay. All right. Well, thank you, Katie.